I welcome Vladimir for this podcast. This is a kind of a podcast where I'm trying to demystify with one of the professionals who has been in the industry over the course of time. That's the industry which is called as a self-driving car. This technology has evolved over the course of time, not like the software has evolved over the course of time or the hardware which we are using is evolving over the course of time. It's every aspect that we are seeing now. Like it can be in terms of the FSD computers which are there from the Tesla, that they just got sick and tired of the same old Nvidia hardware and they just moved on. So today's world has somehow achieved level 3 autonomy. So now what's that work that we need to put in to achieve level 5 and level 4 autonomy is what we will be discussing here. So thank you so much for giving a podcast, sir.
Hi. Nice to meet you. It's really a pleasure to be on your podcast. So
Yeah,
it's exciting topics to discuss. Yeah.
yeah, sure. Like, of course, you have seen technology grow from your academic only, because most of our technology as an encounter starts with our academic journey itself. Like, how was your academic journey and how was the technology during those time? Of course, I know that was an era of Orkut, Hotmail. I think probably Gmail was some extent was there, but like, how has technology evolved over the course of time according to you?
Mhm. Yeah. So it's an interesting question. So let me see. I started working in computer vision and machine learning around, let's say, 2010, probably. So, and I started my PhD then in computer vision end of 2011. And a lot has changed this time. Yeah. So it started like 2010. Basically, deep learning wasn't there yet, or it was in the very beginnings. And there was some papers before that about convolutional networks, but really there wasn't the hardware to get it running. So when I started doing computer vision, especially, it was mostly written by myself. You were implementing some papers. We had some very crappy hardware to run it on. Like we had a workstation, but still mostly CPU. Um, and it was very difficult. Like you spend tons of time preparing your data, writing some functions, debugging something. It was all C++ because you needed to be fast. Yeah, and then things changed quite a bit, especially 2012, I think, was the first paper about the ImageNet, and the first really deep learning paper that kickstarted it all, by Alex Krzyzewski. And there, I think people realized that GPUs are very suitable for this kind of work, and starting putting a lot of effort to bring things on the GPU. And the first years were also rough. There were like many different frameworks, and they weren't easy to use, right? Remember, you're working with Cafe in the beginning, and it was difficult to get it running. I mean, you didn't have all this ecosystem. And when you look where we're standing now, like you have amazing libraries like PyTorch and TensorFlow, and they kind of converged to something they can do very similar things by now. There are differences, but they're extremely powerful, and they're extremely, the ecosystem is so developed. It's so easy now to get started, and everything is free. And I think this work by the people creating TensorFlow and PyTorch like enable this whole thing to explode, because the barrier to entry is so low now. So I think this is let's say on the framework side, on the libraries. Another huge advance has obviously been the hardware, and the capabilities that it gives you to to run complicated models, and to train complicated models, and basically now have GPUs and special hardware like the TPUs from Google that enable very fast iteration, and also on edge devices like in cars. I can remember, like 2010, you had some very specific ASIC chips that could run computer vision, but not deep learning yet. And could process like one camera image that was like 1 megapixel or something. And
Very
now,
less
there's,
frames per second, very less frames per second.
yes,
Oh,
and yeah, exactly, yeah. So, and now you have like, you can easily run like 12 cameras, high resolution, up to 8 megapixels on a chip that goes into the car, right? And many people don't realize, but cars have they have a lot of constraints regarding hardware, because you need to put it somewhere, you need to cool it, and it needs to work from Norway in the winter when it's -50 to Dubai in the summer where it's like 40 degrees, and it always needs to work, and this is very hard to do. I mean, if you just take a off-the-shelf GPU, it just won't do it. So this has advanced a lot as well. Yeah, so basically it's not a problem to run multiple cameras. I mean, Tesla has their FSD computer, but there are similar platforms from companies like NVIDIA with the Drive PX or Mobileye with the IQ chip. So it's something that a lot of people already have. And the third one, I think this is also another important aspect, are data sets and data. And this has changed also a lot. I remember the beginning of my PhD, there were like a couple of very low resolution data sets for computer vision and autonomous driving, like the CamVid data set, which is something like
very old.
640 times 320. It was kind of labeled. They had like, I don't know, something like 1,000. I don't even know if they had 1,000 images labeled. So it's not a lot. And there have been a lot of data sets recently that were open sourced, that really pushed the industry forward. Let's say the Kitty data sets and the cityscapes. Especially cityscapes have been amazing for semantic segmentation. And this enables not only like academics and industry to try different things, to come up with new ideas, to test those ideas. And you don't need like massive budgets to get started. And yeah, I remember in the beginning of my PhD, I was labeling images myself or together with students. It's not nice to label semantic segmentation. Takes about half an hour for an image. So
Yeah,
yeah, so this is really, the industry is exploding, and there have been changes on all fronts, like software and data and hardware. Yeah, so it's an exciting time to work on this.
yeah, it's really an exciting time because data sets are like, it's an open source community now. Just having
Yeah.
data sets, it's like ImageNet, which ImageNet or ImageNet, when people came out with that standard, when you told about the Alex Katauzian's AlexNet, which was giving out such amount of computations, ResNets, a lot of things came out afterwards, and it's an amazing thing. But like, how have you seen the evolution of the neural network architecture over the course of time? Because when you told about AlexNet and everything, they still work on the same old principles that happen in a game computing, which is
Mhm.
convolution at the end of the day, and convolution neural networks are there. And there are flavors of convolution neural networks which are coming up, like ResNet. There are other flavors of it, like it's evolving over the course of time. Have you seen this evolution of neural networks over the course of time?
Okay, yeah, let me try to see how I summarize it best. So I think you see, let's say since 2012, obviously everybody in computer vision said this is the way to go. You saw it in the conferences. Certainly from 2013, 14, everything was deep learning. It was challenging to publish something that was not deep learning. It was possible, but yeah. So first, everybody in computer vision went to convolutions, right? Because it's like the perfect, yeah, it's perfectly suited for that, because it can generate the features for you. And so let's say academics, they try to find new architectures. They try to experiment with different types of layers, different types of optimization techniques, regularization techniques, and specializing in different things. Like you had this RCNNs for object detection. You had the UNet architectures, let's say convolution, deconvolution for semantic segmentation. So they kind of split towards different kind of tasks. and there were like sub communities for them because the networks were kind of different. And they were like people started doing very extravagant architectures. But I think in industry it's a bit different, right? Because it's not about having the fanciest architecture. You need something that really works and works fast, because in the end, you usually want it to work in real time, especially in self-driving. So it's been more about the data there. Like you need some stable foundations, but the real challenge in industry is to get the data, to get the right data, to get the right data labeled, to correct label errors, and clean your data set. Because there was a really interesting paper published recently by MIT. They reviewed the labeling of popular data sets, including ImageNet, and found something like 5, almost 6% label errors on ImageNet. You know, in industry, in academics, people don't care that much about it. You know, it's a benchmark, everybody uses it, so just use it and see what comes out. In industry, you care about the end performance, right? I care about when I put it in the car and drive out, that it works and works good. So I think this has been like kind of a two parallel paths. You know, industry academics tries some fancy architectures and they iterate there. Industry is more focused on getting this whole thing to production, which is kind of different skill sets. And there are always like things that from industry, from academics, they make it into industry. Like for example, ResNets, it was really a breakthrough in the way that it enables you to train deep networks, right? Such breakthroughs happen all the time and they make their way into industry. Yeah, and there is a recent trend about transformers, right? So it's kind of transformers start replacing convolution slowly. So I think this is the next big trend you see. Like transformers got very popular with language models. And now people said basically, why don't they try it on images? And there have been papers that show you that the transformer actually learns to be better than convolutions. There is like the problem is usually they need much more data. But I think this will get solved also over time. So I think this is kind of the next wave coming with everybody using transformers for vision. And there are already a couple of very nice papers from Google, from Facebook, still like needing huge amounts of data. But I think this will change it. But this is very exciting to see where this will lead us.
Yeah, you know, over the course of time, we have seen like neural network architecture evolve, but like, you know, there is a huge way in which sensor suits have actually given a lot of changes. Like I'm saying in terms of lidars, which were actually seen like this has to be the must be a sensor on a self-driving car. Tesla actually shattered the dream of all the other scientists who said that lidar is the only solution. They said radars can do the job. Like, what do you think about the sensor suits today? Like, how are they evolving over the course of time? Like, I'm talking in terms of software aspects, which still run those sensor suits. I'm also talking about like sampling rates. You know, sampling rates are increasing, like huge thing, like lot of things. Like, what do you think about the sensor suits these days, which are put on your entire self-driving car?
Okay, yeah. So let me split this in two. I want to talk about cameras separately from radar and lidar, and you'll see why. So cameras, they're one of the oldest sensor. I mean, radars are also used for quite a lot of time in self-driving, but or in driver assistance at least. But cameras are much more versatile. They can detect much more information. It's like radar is very good at measuring distance and detecting objects, but that's about it. If you want to recognize a traffic sign or traffic light, you basically need a camera. So how cameras change, they increase in resolution, obviously, increase in frame rate. But I think the most important thing is the increase in dynamic range. Like when you're outdoors and when you have the sun lighting, and you have strong shadows from buildings, this is a very challenging environment to not overexpose some of the images. And if you see the first Kitty images, they're actually quite bad in this because they didn't use a high dynamic range camera. And the cameras you have now, you have no problem seeing the same and shadows and strong light. Also at night, it's also challenging because you want to see like a pedestrian like crossing from the street in the dark. So you need very good low light performance, and you also want to see bright objects like traffic lights and stuff like this. So this has been a huge increase, and obviously you can now put cameras all over the car to have a 360-degree view, and have some telecameras that look further away. So just the ability to put more and more cameras has been amazing. But I would say nothing fundamentally changed in how people interpret the camera images, because say the camera image is a lot of raw data. You need to extract some features from it, and it's very difficult to code this manual, like say, okay, if I see an edge here and an edge here, this is the person. This doesn't work. Right? You need machine learning. So this didn't change a lot. This is a different thing for radars and lidars. Like in radars, there is you can do a lot of things, but it's manual algorithms, let's say, because the traditional radars, they're very low resolution. And people use some kind of machine learning techniques, but you don't have much data, right? And what deep learning really shines is when you have a lot of unstructured data and can extract the best features that no human can think about. So this is what's changing now in radars, for example, with the so-called imaging radars that provide much higher resolution. They can have the much better capability to distinguish objects from each other, because this is also something that's a problem when you have two objects close to each other. It's very hard for the radar to distinguish. Or if you have like a object under a bridge, I mean, you can actually see these Tesla videos how they're braking under the bridge because they are slowing down before the bridge because of false positives. And this is changing a lot. And what happens when you get a lot of resolution, you get a lot of data, a lot of unstructured data. So now the only way to process this, because again, computer vision, not computer vision, but machine learning techniques, actually similar to computer vision. It's the same with lidars, right? You have the velodynes on top, and you can do some clustering, or you had this, many cars have this small lidars that have just a couple of rows, like our production Audis now have some of these lidars, which are very simple, and you can build some clustering. But you now see, I mean, the lidar industry has exploded in the recent years, and I'm not only talking about the 360 lidars on the top, but they are like integrated solid state lidars that you can put in the rear of the car. So you can really integrate them in production cars that have amazing resolutions. It's almost like a camera image. So again, that's what happens, is that you basically have no chance to do it without deep learning and such algorithms. And so this is exciting. The resolution of radars and lidars increased so much that it kind of already you need to adapt. You have no chance to do anything without machine learning. So this is exciting.
But like, you talked a lot about the computer vision, the algorithms which can work on these approaches. But like, I want to ask you this one question: can we make neural network reason everything tomorrow? Like I'm saying, in terms of, I can see you virtually, I can see you as a person in such a way that when something as a poster is there in front of, and I was seeing a video from Tesla. Tesla really recognized and poster of a person as a person, like like it doesn't have that intuitive level of understanding. Like I and you can talk and we can really reason out some things which we have not learned. Like I don't know you personally as a professional, but I know you as a person because I've attended your webinars and kind of things like that. But like, can they really made to reason like everything tomorrow, like inside, intent, everything?
Yeah, I think this is a great question, and I think we're not there yet. I think this is the problem. So deep learning is now very good on very narrow tasks, very specific tasks, but they still cannot really generalize well. So they're only good at the task you give them. So as you said, the deep learning is good to say, is this a person or not? And it cannot recognize that this is a live person walking on the street or just some kind of image. It looks like a person, so it thinks it is. What you need there, what you do as a human, you have much more context in your head. You have much better understanding at the whole scene. This is a poster, and this is a poster because people make ads, and people make ads because they want to promote their products. This is all in your head, and it's automatically applied there when you do it. So and this is, I think this is something that machine learning is still not there yet. Like, this goes a little bit toward the aim of general artificial intelligence, which I think we are still far away. And that's the point where, there's been a lot of arguing. Like, Elon Musk obviously says, okay, you only need vision. And his argument is good. I drive only with my eyes. I have no LiDAR, I have no radar. So why shouldn't a neural network be able to drive in the same way? And but on the other hand, neural networks are not there yet. So basically, this is a gamble on computer vision technology, machine learning advancing enough in a short period of time that they're good enough. And I'm not sure it will work, right? We'll see. But so other companies are saying, like, technology is not there yet, vision. So we need to take every possible sensor and build as much redundancy as possible to be able to guarantee the car is safe, right? And this is the approach that almost everybody else takes. Build the right LiDAR, radar. There are the hardware is there, the sensors are there, and if they might make your car safer, why not use it, right? So we'll see it. I mean, Tesla obviously has great people. They have lots of data, so I think they are in a good position to advance the technology. The question is, can they advance it enough in the next 1-2 years, or does it take 20 years? I don't know.
I think we talked a lot about the professional aspects of this technology, and we actually talked a lot on things which we really wanted. But like, how is the public perception on this technology? Because BMW is known for luxury. BMW is known for the infotainment technology. I think probably these were some of the technologies that I really didn't see in some of the other cars or any other bikes also. I saw it in BMW. Like, how is public perception over the self-driving car technology today?
Okay, so I mean, yeah, this is my personal opinion, and I think there are two aspects. People talking about self-driving sometimes mean different things. Most people usually imagine this kind of a robot taxi, or you're not in the car and imagine, you send your car to school to pick up your kids and drive them back home or whatever. And I think this is too abstract, too far away. And everybody says, yeah, well, if one day this comes, it's cool, but it's too far away. And then the other aspect are, let's say, level 2 systems that are already there, and they increase comfort and safety. And for example, now a lot of people don't know this, but there is an organization in Europe, and there are similar organizations all over the world called Euro NCAP, that they're famous for the crash tests. They crash the car and see how well you survive, basically. And they have now very strict tests for driver assistance systems. The systems that keep you on the road, recognize the speed limits, automatically brake in other cars. And this is more or less mandatory. So you cannot get more than 1-2 stars if you don't have all the systems, and they test them. So this is something that already has today impact on safety, and I think it's a great thing because these systems really help. And the other thing is comfort. Like a lot of people say, BMWs are driving machines for drivers to have fun and so on. Why do you put um, like autonomous driving on them? And so again, this is my personal opinion, but there are situations where it's very fun to drive yourself, like on a twisty mountain road or on an empty highway in Germany. But it's not fun driving in a traffic jam, right? It's just no fun in driving, and the fun in driving is then to let the car take over the driving, so you can do something else. So I think this has a lot of value, and even level 2 systems. I have one of these in my cars, and it's very relaxing in the traffic jam. That you still need to pay attention, but what if the car takes over from you, and you can listen to a podcast or something. So it's already there and already has impact, and it will only increase. But I think people approaching it from both ends. Like traditional car manufacturers have the driver assistance functions, and they make them safer and more automated. And they're like the other companies, usually like technology companies like Tesla, Uber, Lyft. No, sorry, not Tesla. I mean Waymo. So Tesla is something in between. Tesla is something special, but they try to do the robotaxi thing, straight to level 4, level 5. So different approaches there. But I think a lot of people disregard, let's say, the level 2 self-driving systems, and they are there today, and they have big impact.
Yeah, that's sure. That's sure that people are very nicely inclined over the luxuries that they are getting in BMW or any cars, but they still have that mindset like, I've given money for that car and I need to be sitting like a king. Like, why should I be take all the pain of driving? I think probably public has different perceptions over the self-driving car. Over the course of time, I think people are going to really understand the purpose of building a self-driving car and actually giving that sort of an intelligence to a machine. Yes, for sure. But like, so through your webinars, not webinar, I actually attended one of your webinar and it was so nice to just be there. Like, what's your approach when you're solving a problem when it comes to computer vision? Of course, you have done your master's, PhD. Yeah, where basically you are more into an academic stress, like I need to write my exams, I need to get this amount of breakthroughs in my research in order to get a PhD, things like that. But like in professional life, I think it's a different story, because a lot of people are like, I have talked to a lot of professionals and they just say that we don't care about the optimization to that extent, because we don't care throwing the CPU, GPU or CPU cycles. And like, how is it different from academic and the professional life in approaching any problem statement? Like, I just want everything related to that, approaching a problem statement.
Okay, yeah, I can talk about it. And I've seen both worlds, because I did my PhD, and of course, doing a PhD is something that you do at the university, right? But I did it in cooperation with BMW. So it was like sitting some days in the university, some days in BMW, and they kind of have different goals. Like university wants to publish papers, and to publish papers, you need to have something novel, right? If you just get a new data set, use it and get good results, this is not enough. You need to some new approach, something new. And industry doesn't care about papers that have some theoretic insight, which is not
Algorithms or something
applicable to
like that.
practice. Yeah, I mean, if it takes 2 hours to process an image, it's not going to work in industry, right? Or it's going to work in 10 years or 5 years when you have the hardware. So this was, for me, this was a little bit of a challenge. So my approach was to, push, have some new ideas, push them to industry, but always look at the core, like a problem that I can apply it to. Like in my case, it was semantic segmentation, and I applied it to the problem of traffic light detection. So it's kind of possible to do both, but there are, of course, people focusing on one. And so, so you asked about how you approach the problem in industry, and it's the only thing you care about is what your customer sees. I don't care about detection rates of traffic lights. If it doesn't translate into a better function. And I can try to give you one example. So I think it's better to understand. So I worked a couple of years ago on a function that when you drive your car and you approach a red traffic light, and if you're too fast, it will give you a warning. So it will it's first show you a red traffic light and then give a sound. And this is already in cars for 2 years now in BMW. So, and it actually really helps from time to time. And so obviously you need some kind of traffic light detection. You need to detect the traffic lights. And of course you say, yeah, I need high detection rate and I need high false positive rate. And this is the typical things you optimize in academia, right? And you make a paper where detection rate is 10% higher, and it's great, and you can publish a new method. But it turned out we had the problem, like there were people working on the traffic light detection and made it better. Detection rate increased a lot, false positives increased also a little bit, but it was good. And we drive out and it's actually worse. Right, because what happened was that they increased the detection rate of some traffic lights that were far away, and when you approach a traffic light, you only care about the next traffic light you have in front. I don't care if you have a traffic light 50 meters in front of that and I need to give the warning. I don't care if you detect the traffic light 200 meters away. So, but if you increase the false positive rate a little bit and you start detecting red traffic lights where they're known, you have false warnings. So this was one example of how this typical computer vision metrics used in academia, they're not useful at all in this case for a function, because in your function, what the customer sees, he cares about getting the warning, right? And not having false warnings. So we had to work a lot to define some metrics that actually correspond to what the driver sees. And we optimized heavily, for example, into not giving false warnings because you don't want your car doing pee pee at every junction. So it was challenging to match these two worlds, but it's possible. And so this is like when you're in industry, you care about what your customer experiences. It's often not what your computer vision model outputs. Right? And other things are like, so this is one aspect. When is your model good enough? And there are other aspects like, does it work everywhere? Right? Their traffic lights look different in Germany and south of France and south of Italy. And there are a lot of different situations. So this is the other challenge, to make it work everywhere, not on the data set of like 1,000 images that you can optimize and overfit on, or it needs to work everywhere. And we had test drivers spending many days and weeks driving all over Europe to be able to validate this. And this is the other challenge. Like getting to 90% on a small data set is easy. Getting it to work everywhere, in at day, at night, at rain, at strong sun. This is the real challenge. So this is there are a lot of iterations on the data. You connect new data, label it, try new situations. This is what academia usually doesn't do, right? You have your data set, that's it, and you make it work better. It's usually, when you have comparison with other papers, usually not an option to say, okay, I go out and label some more data. Some people kind of do it in some data sets, but no, we have a very specific problem and you optimize on it. So you look the situations that will improve there. So this is a very different approach in academia. In academia, I was using my data set, running experiments. In academia, usually fiddling with the model, you try different architectures, you try different hyperparameters until it works best on this data set. In industry, usually working on the data side. We have a problem, how can I get new data? How can I get it efficiently? How can I label it efficiently? How do I find the right data to label? So this is more of the challenge. So it's actually very different, right? And And maybe the last aspect here is when you're ready. So say, okay, in academia, you have your model, you publish your paper, it's all fine. In the real world, you also optimize, you reach some performance, and you roll it out to all customers. But then you're not ready with that. We have also worked on a system that recognizes speed limits, and we did it. And you know what happens then? In the United Arab Emirates, they decided to put 160 kilometers per hour speed limits. Our network has never seen anything like that. There are no 160, and we never thought somebody will come up with this, but they do, and we have a problem there because it doesn't recognize it. And then the customers go to the dealer and start complaining and say, yeah, I paid so much for this car, why doesn't it recognize it? So you now need to update. So you need a way to monitor your system in production, see if it performs well, or because the world changes and then your system will potentially get worse. So you need to be able to iterate. Oh, when it's in production, you constantly need to see how I get new data, how I label it, how I recognize automatically that I have a problem. And this is another challenge that academia usually doesn't care about, right? Papers out, you presented at the conference, and yeah, you're ready. So it's different aspects. Academia also, I mean, it's a very valuable work because a lot of the breakthroughs come actually from academia and make it into industry, but it's just different, two different things.
Yeah, that's true. That's true. Because in academia, me myself, I just want to just go to the best university that I can afford to. So what I now target is the number of papers that I'm publishing right now. So
Mm.
it's a different approach when you're in academia, and when it's in professional life, I think probably it's going to be a whole new level of approach that I should be giving, because I need to improvise on myself. I mean, thank you so much for this amazing podcast, sir. I didn't expect this to happen at the fractions of time. And I think if I had done this podcast that day, the previous recording, probably we wouldn't have got this insight out from you. Thank you so much, sir. Thank you so much.
Yeah. Sorry, I was. Yeah, it was really stressful, but today is actually the perfect day because I have a day off. My son's in the daycare, so it's much easier.
It was an honor to have a podcast with you today. Thank you so much, sir. Thank you so much.
Okay. Yeah, I'm happy. I think it worked out better this time. Yeah.